Hi, my name is John Hoban, and today I'm going to be talking to you about my work on software for attitude determination and control systems on CubeSats. This past summer, I was a member of the Oregon Small Satellite Project, which is a team looking to build and launch Oregon's first satellite. This organization is based in Portland State University in Oregon, but it has attracted the attention of students all over Oregon, and in my case, all over the country. So the satellite that we're building, we're calling ORSAT. And ORSAT is a CubeSat nanosatellite, which is a pretty common form of nanosatellite that amateur aerospace teams will build so they can put their own satellite into space. ORSAT will carry two primary mission payloads. The first is called ORSAT Live, which will allow people on the ground to request a live video stream of their position on the ground from space courtesy of ORSAT's camera. The second is a cirrus flux camera, which will allow ORSAT to take images of cirrus clouds in Earth's atmosphere. Now, as you can imagine, both of these payloads require pretty precise adjustments in ORSAT's rotation or attitude in orbit so it can properly point its camera in the right direction to, take a picture of that specific area. So this is where an attitude determination and control system, or ADCS, comes into play. On any satellite, not just ORSAT or a CubeSat or nanosatellite, ADCS is responsible for obtaining a satellite's attitude and position in orbit and then responding by making any necessary adjustments in attitude based on what the satellite is doing at the current moment, what it's taking a picture of, what it should be pointing at. So ORSAT has plenty of devices and instruments on board that allows it to measure and make these adjustments, but when I joined the project, it needed some software to get all of these instruments to talk to each other properly. My work on the ADCS software was to ensure that data was flowing across this board and between these instruments properly, and also making sure that any other processes on the ADCS board that needed data from these instruments was getting it properly. So without any further ado, I'm going to walk you through my design and implementation of the ADCS software by showing you a few diagrams.
This is a block diagram of all this software and hardware on ORSAT's ADCS. On the left side are the instruments that I mentioned before that need to send and receive data from the ADCS board. What exactly they do and how they work is beyond the scope of this presentation, but it's most important to know that the inertial momentum unit, magnetometer, and GPS are responsible for data collection, and the reaction wheels and magnetorquers are responsible for making attitude adjustments to ORSAT. On the right side, the SDR, GPS, and ADCS card is the most important part. That is where the software that I worked on will be. The A8 designation means that the software runs on an ARM Cortex A8 board running Linux. So naturally, the development I had to do was on Linux using a Ubuntu virtual machine. Furthermore, all of the source code is written in Python, so naturally that was my language of choice. Now, the software on the ADCS card is split into three main modules: a library, a manager, and a 42 interface. It's worth mentioning now that I did not work on this software package alone. I had the help of two ORSAT interns. Corey Gillette was responsible for writing the entirety of the library, which I'll touch on briefly, and Ryan Medic helped write the framework for the manager and set up its basic design. The overall design and implementation of the manager and 42 interface, however, fell to me. So now I'm going to briefly explain what each of those three modules do. This block diagram contains both the ADCS library and ADCS manager daemon. Let's start with the library. This contains modules that calculate satellite properties that are used elsewhere on the ADCS board. The library converts mission data, sensor data, and ORSAT's current state into commands that are passed to the magnetorquers and reaction wheels so they can make their necessary attitude adjustments. The library also has a simulator that propagates these commands and outputs several vectors that describe the satellite's state afterward. Looking at the block diagram, the state machine, magnetorquer controller, reaction wheel controller, and call-in filters all fall under the ADCS library. Essentially, this library is responsible for all the calculations that happen in ADCS. Now moving on to the manager daemon, which is where my work began. This handles all data flow on the ADCS board, and it does this in the form of a daemon. The manager hosts a dbus server, which is a way to quickly communicate between different processes on a Linux board. This dbus server, which on this diagram is listed as the dbus adapter, fetches local board data and asynchronously fires data signals that can be retrieved by other processes that need this data on the ADCS board. An example of a process that would need this is the 42 interface, which I will get to in just a moment, and also the magnet torquer and reaction wheels, so they know exactly what their next move should be. The ADCS manager really is the heart and soul of ADCS's data flow. Now onto the ADCS 42 interface. 42 is an open source spacecraft attitude simulator and visualization software. Within ADCS, 42's RX subprogram is used to watch a virtual ORSAT respond to different magnet torquer and reaction wheel commands during testing, just to make the whole process easier. This interface is responsible for formatting simulation data received from the manager daemon and sending it to 42RX. Essentially, this interface spawns its own dbus client that connects to the dbus server that I mentioned earlier, formats it in a way that 42 can understand, and then sends it to 42 via a socket. That concludes explaining ORSAT's 3 ADCS software modules, but personally I find the block diagrams alone a little hard to understand, so now I'm going to show a demonstration of ORSAT's ADCS software via 42. 42 I think is the best way to show how ADCS works because it's the only part of ADCS that actually produces any output. So what I just did there was launch the ADCS manager daemon, which you can't see running because it doesn't actually produce any output, but the dbus server is up, it's sending data signals to any processes that want to receive them, which 42 is one of those processes. So I will now launch 42, which will be up in a few seconds. Okay, so this is what 42 looks like. The camera that you're seeing is a rough idea of what ORSAT would look like when it's actually in orbit if it were responding to this state data, which the state data I'm talking about is in this terminal below. These numbers are what's actually powering 42, and these are the numbers that are being broadcast from the dbus server on the ADCS manager.
So in terms of results for this project, the Python source code was debugged on my own virtual machine and runs without error there. However, it's currently being tested at the developer boards at Portland State University, so if the code happens to run differently there, more debugging will be required. Furthermore, the ADCS library is still being updated, so if anything that gets changed there requires updates to the manager or 42 interface, those updates will just have to be made. So that's it for this presentation. I hope you enjoyed my discussion on ADCS software design. My hope for my work is that a team looking to build a nanosatellite in the future will look back at this scheme and tweak it and be inspired by it for their own code. Thanks for watching.